Okay, let us see here the mechanism of radial bending in ionosphere. Mechanism of very important topic, the mechanism of radial bending in ionosphere. Okay, so what you are saying in an ionosphere? In an ionosphere, this is my earth surface. Let us consider this is my earth surface. So this is my ionosphere. Okay, so it is extending from 50 kilometers to, it is extending from 50 kilometers to 400 kilometers. Okay. So this is my transmitting antenna. This is my receiving antenna. Okay. So what happens if I transmit any signal? If I transmit any signal from ionosphere, from at the surface, whose frequency is in between, whose frequency is in between, whose frequency in between 2 megahertz to 2 megahertz to 30 megahertz. So what happened when I transmitted? It enters into the ionosphere and it is getting back reflected and coming here. How this wave, whatever you have transmitted here, how it will bend back and come to the receiver. What is going to happen in this ionosphere? What is going to happen in this ionosphere? Okay, so we know that there are different layers here. There are different layers in ionosphere. Okay, so which layer is more highly concentrated? F2 layer is highly concentrated. So coming to the electron density, coming to the electron density, coming to electron density, number of electrons present in F2 is greater than number of electrons present in F1 layer is greater than number of electrons present in E layer is greater than number of electrons present in D layer. Okay, so the number of electrons per cubic meter, the number of electrons per cubic meter is very less in D layer when compared to F layer. Okay, now let us take the refractive index formula. U is equal to, let us take the refractive index formula. The mu is equal to, the formula for the refractive index is mu is equal to, what is the formula for the refractive index? Mu is equal to, I have derived that mu is equal to root of 1 minus 81 n by f square. Okay, so if I substituted this, okay, so in which layer the number of electrons are more? Here in F2 layer. Okay, so if I substituted the number of electrons in F2 layer, means if n is high, 1 minus, what happened to the value of refractive index? The refractive index is getting reduced. If the number of charge carriers are increasing, if the charge carriers are increasing, the value of U decreases. Okay, so the same thing if I substituted here the number of electrons in F2 layer and the number of electrons in D layer. So no doubt the number of electrons in D layer is less when compared to the number of electrons in F2 layer. So coming to a refractive index, coming to a refractive index. Okay, so the same thing if we substituted, a refractive index of D is greater than a refractive index of E is greater than a refractive index of F1 is greater than a refractive index of F2. Okay, so this is the thing you want to remember. Okay, so clear? So as I am going from bottom layer to upper layer, what happened? Electron density increases. Electron density. Okay, that is N. Number of electrons per cubic meter increases. At the same time, when I am going from bottom to top, what happened to a refractive index? A refractive index decreases. Refractive index decreases as I am moving from D layer to F2 layer. The refractive index decreases, whereas the electron density increases. Okay, so these things you want to remember. These things you want to remember. Very important thing. Okay, so n of f2 is free, and this one is free. Okay, so now let us take the expression mu is equal to root of 1 minus 81 n by f. So note out from this expression, the value of mu is always less than 1. Okay, the value of mu is always less than 1. Okay, the value of mu is always less than 1. So here, the bending of the ionosphere, can we understand why the help of refractive index formula. Okay, so mu is equal to 1 minus 811 by f square. So the refractive index is always less than unity. Okay, if the charge carrier density is higher than frequency, if the charge carrier density is higher than frequency, means that is if 81n is greater than f square. Okay, so what happened? Then the refractive index becomes imaginary. Then the refractive index becomes imaginary, which means in such a condition, the radio waves are attenuated. Okay, in such conditions, the radio waves are attenuated at this frequency, and the ionosphere is not able to transmit or bend the radio waves. Okay, so if 81, if number of charge carriers are greater than f square, then it becomes imaginary. Okay, so the bending of the, let us see how the wave will get bend in the ionosphere. Okay, so the bending of radio wave, the bending of radio wave by the ionosphere, is given by or is governed by ordinary optical ordinary optical law, that is Snell's law. Snell's law. Okay, what is Snell's law? Snell's law gives is equal to sin I by sin R. It gives the relationship between angle of incidence angle of incidence and angle of angle of reflection. Angle of incidence and angle of. Okay, so from this expression, it is clear that the value of mu is always less than 1. Okay, from this, if mu is less than 1, what can we understand that? Okay, sin R is greater than sin A. Sin R, so is greater than sin A. Okay, so from this, if mu is greater than 1, we can came to understand that mu is sin R is always greater than sin I. Okay, sin R is greater than, means angle of reflection is greater than angle of incidence. Okay, so the angle of incidence is greater, the angle of reflection is greater than the angle of incidence. Okay, so what happened? The angle of reflection goes on deviating from the normal as the wave enters into the rarer medium. Okay, so the wave enters into the rarer medium. The angle of reflection goes on deviating from the normal. Okay, so let us see here, for example, this is my earth surface. This is my earth surface. This is my earth surface. It assumes of the various layers of ionosphere. The various layers of ionosphere. Various layers of ionosphere. Okay, for example, this is my transmitting antenna and this is my receiving antenna. This is my transmitting antenna and this is my receiving antenna. Okay. Now let us consider the wave is entering from the wave enters. This is my ionosphere. So this is my ionosphere. Okay. Now let us then consider the wave just enters into the ionosphere and it enters into the ionosphere at point P. Okay. The wave enters into the ionosphere at point P. Okay. So we have already seen that uh, refractive index of n of f2 is greater than n of f1 is greater than n of E is greater than n of D. From this, refractive index of D is greater than refractive index of E is greater than refractive index of F1 is greater than refractive index. Means the wave is entering means refractive. If you observe here, the wave, for example, this is D layer, E layer. So refractive index of D and this is refractive index of E. So if you observe here, this is the surface, the wave enters into the denser medium to rarer medium. Okay, so this D layer is denser medium and this is rarer medium. Okay, whenever, so let us take here, let us take some few cases here. Let us take some few cases here. This is D layer, this is E layer. This is E layer, this is F1 layer. This is F1 layer, this is F2 layer. Okay, so this is denser medium, this is rarer medium. Okay, whenever the wave enters into the D layer, so the wave will goes on deviating. The wave goes on deviating. Now this signal comes here like this, the wave further deviate. Okay, now so with other color. For example, so see here. Now, whenever the wave enters, this is denser medium, that is, the wave will uh, deviate. Okay, the wave will deviate. Now, this wave enters into the E layer, and when it enters into the E wave further deviate. Now, the signal now it enters here, it comes to critical angle. Okay. After, for example, let us F2 some F21 and F21 and F2. Okay. Now the wave coming that angle of critical impedance now it will comes back. Okay. So like this. So whenever it enters, it deviate, 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 and at one point it will become critical point. At one point, it will become critical frequency. Okay, so critical frequency means you have to let us consider that at point. Yeah. Okay, the wave starts reflecting coming back. Okay, reflecting coming back. It will be just to the receiver. Okay, so as the refractive index as the means the wave is entering from denser medium to rarer medium. Okay, so denser medium to rarer denser medium to rarer medium. The wave, as the wave enters at the point, say, let us point P, point P will be deviating more and more, and a point will reach where it travels parallel to the earth, that is critical angle. Okay, so this is the angle of incidence at which the wave will be parallel to this is your earth surface. So due to parallel to the earth. Here the angle of reflection is 90 degrees and point PM, this is my point PM, this is the highest point in the ionosphere reached by the radio. Okay, okay, so and at that point, okay, at that point, what is the expression? Mu is equal to sin I by sin R. At that point, the angle of reflection is 90 degrees. So mu m is equal to, it will become sine im. This is the highest point. Mu m is equal to sine im, since the angle of reflection, that is critical angle, that is angle of reflection R is equal to 90 degrees. Okay. So the point PM usually is called as point of reflection, although it is actually a point of reflection. Okay. So at this point, the total takes place. What is meant by total internal reflection? Total internal reflection means if you even though transmitted at the same signal, it will present in the same layer. Okay, here the radio wave enters at a point B and leaves the ionosphere at a point Q. Okay, it leaves the it enters at point P, and this is the maximum distance that it enters or penetrates into the ionosphere and leaves the ionosphere at a point Q. Okay, so this is how the wave will get bent back and comes to the receiver. Comes to the receiver. Okay. Now let us